Well, hey there everybody, Mr. Carlson here, and in today's video we're going to talk about valence electrons, and how we kind of group things in the periodic table based on valence electrons. Now, here's the thing. We're going to use this blank periodic table today because this is hopefully going to help us understand this idea of valence electrons. So, first of all, let's make sure we understand when we're talking about the valence electrons of an element, the valence electrons, what we mean is the electrons in the last energy level. The electrons in the last energy level, or we could say the highest energy level. So for example, let me just pick a random element here. Let's go with nitrogen, which would be right here. Nitrogen, which is right here. If I were to write out the electron configuration for nitrogen, let's do that. So let's write out the electron configuration for nitrogen. If I were to do that, so remember we're starting over here. We've got at the first energy level, and we're going to count 1s1, then 1s2, so 1s1, or sorry, did that backwards. We're just going to put 1s2, right? So 1s2 is full. That orbital is full. And then we go to the second energy level, 2s1, 2. So that is full as well, 2s2. And then we would go over here to 2p, because we're now filling up the p orbitals here at the p block, 2p1, 2, and 3, 2p, 3. Now if I look at this, the valence electrons here, just based on this electron configuration, are the electrons that are in the highest, or the outer energy shell. So if I look at this, I've got a 1s orbital, I've got a 2s orbital, and I've got 2p orbital. So the highest energy level here is going to be 2, right? That's the highest one that nitrogen has, is the energy level 2. And if I count up how many electrons that it has 3 electrons that are in p orbitals, and it has 2 electrons that are in s orbital. But those are all at the second energy level, right? And so I have 1, 2, 3, 4, 5 electrons. 5 of the 7 electrons that nitrogen has, 5 of them are valence electrons, or outer shell electrons is sometimes what they're called, because those electrons are at the highest, or the outer energy level, the energy level 2. And we could do that for any of these elements in here, okay? Now, here's the thing. Some patterns that will develop here from, let me just get rid of these real quick. There are some patterns that develop within the periodic table. If we look, we talked about the other day that we've got the periodic table will break up into these periods. These are our period numbers here. So period 1, period 2, period 3, period 4, so on and so forth. And again, what those are showing, so for period 1, the elements in period 1 here are filling up that 1s orbital. Period 2 have electrons that are filling up the 2s orbital and the 2p orbital. For period 3, they're filling up the 3s orbital and the 3p orbital. For period 4, it gets a little more complicated. They're filling up the 4s orbital, they're filling up the 3d orbital, and then the 4p orbital, so on and so forth. That's what those are signifying. And then we've got the group numbers here. Remember, the group numbers, what those are going to show us in this case, these are going to show us the amount of valence electrons, except for this group right in here, so our transition elements in here. So for these in here, and then some down here underneath that staircase that we have. So let me quick draw in that staircase here. So remember that our transition elements go from here all the way to the edge of the staircase here. We've got our transition metals, our transition elements. We are going to, for now, when we're talking about valence electrons, we're going to leave the transition metals out, because the transition metals, I'm going to draw a line across here. And remember, that includes these down here. Our transition metals have different rules for valence electrons. So transition metals have varying, we'll say varying amounts of valence electrons. And so it really has to do with these 3D orbitals, which kind of throw things a little bit off. Those 3D orbitals kind of throw things off. But we'll get to those a little bit down the road. For now, we're just going to kind of ignore those transition metals when we're talking about valence electrons. But we'll come back to it. Instead, what we're going to look at is our representative elements. So our elements that are in these two columns here, and then these columns over here to the right of this staircase. And in some periodic tables, what they have drawn at the top above each group number is they have this. They'll have 1A, 2A, 3A, 4A, all the way across, just like this, and 8A. And what those are essentially signifying, again, is this number here is signifying the number of valence or outer shell electrons. So if I look at group 1 here, group 1, which has hydrogen and lithium, and I'm drawing a blank all of a sudden, sodium, potassium, so on and so forth. Okay, those elements in group 1 here, these elements in group 1 all have one valence electron. Same thing for group 2 here. So again, here we would have beryllium, we would have magnesium, we would have calcium. All of those elements in group 2 have two valence electrons, two outer shell electrons. And same thing for these groups over here. So if I were to look at in group 8A here, so I've got helium, I've got neon, I've got argon, krypton, xenon. These guys all of them have 8 electrons in their outer shell, in their very last shell. Now, they all have different amounts of electrons before that outer shell, right? But it's that last shell, that very last, that highest energy level where they have the same amount of electrons. And that's what we notice. That's one of the patterns we get in the periodic table is that, so all of these have the same number of valence electrons. That's important because, and that's why we see this pattern, is because valence electrons, which are basically responsible for most of the chemistry that we see, all the bonding that we see happening between elements, is because of these valence electrons. And so that's why when we look at the periodic table, elements that are in the same group have similar chemical properties because these all have the same valence electron structure. So let's think about it like this. Let's draw, we'll look at group 2 here. So if we look at group 2, let's draw out the electron configuration for beryllium, magnesium, and calcium, and we'll just do noble gas configurations. So for beryllium here, I'm going to have He, so He for its noble gas, that's closest to it. And then filling up from there, so from He goes to the second energy level, so 2s and then 1, 2. There's the noble gas configuration for beryllium. If I do it for magnesium, so follow back to neon, and now we're at the third energy level, so 3 s block, so S1, 2. Once again, S2. We'll do it for calcium, so that would be argon, and we would go to the fourth energy level, and then again still in the S block though, S1, 2 for calcium. And you should see a pattern, right? If I were to keep going down for each of these elements, if I could remember these ones off the top of my head, I think it's strontium, I can't remember. But anyways, if you were to continue doing that, you would notice there'd be an S2 at the end of each electron configuration for all these elements here in group 2, they would all end with S2 because they all have 2 electrons in their outer shell, in their last energy level. Let's look at, for example, we'll look at over here. We'll do this group here. So here we've got fluorine, chlorine, bromine, and iodine. We'll look at these ones. So let's say we were to do the electron configuration for fluorine. So we would have helium, and follow that again all the way to fluorine now. So from helium, then we'd go 2s2, 2s2, and then jump over here, and we'd have 2p, 1, 2, 3, 4, 5. Let's do it for chlorine as well, so that would be neon. Then follow that to chlorine, so neon would go 3s2, 3s2, and then jump over here to 3p, 1, 2, 3, 4, 5. 3p, 5. Let's do it for, we'll just do it for bromine next. So argon is the previous one. Follow that over, 4s2. And then now we're going to go, we have the D block in here though, right? Remember that starts at the 3rd energy level, so it would be 3d10, 3d10, and then we would go to 4, move this over a little bit, 4p5. Okay, now just looking at these, right? Just looking at these, we'll notice that, again, just like in the previous ones, right? Each of these elements in this row has 7 valence electrons, 7 valence electrons. Because if I look at the configuration for fluorine here, right, these are both in the 2nd energy level. And so I've got 5, 6, 7 electrons at the 2nd energy level, which is the highest energy level for fluorine. For chlorine, the highest energy level is 3, the 3rd energy level, and I've got a total of 5, 6, 7 electrons in that 3rd energy level. But now let's look at bromine here. Now for bromine, bromine has a full D sublevel, right? But remember that D sublevel starts at the 3rd energy level. And so if I look at the valence electrons, which are at the highest or the last energy level, right? I've got this 4 here and 4 here, and so I'm looking at just the 4th energy level here for the valence electrons. But again, it'd be 5, 6, 7 valence electrons, just like this one and just like this one. If I were to do the same thing for iodine, I would have the same thing. I would have 5s2 and 5p5 and 4d10, but it would be the same valence electron structure basically. So the main thing to remember here for these valence electrons is that we're looking at the group number here at the top to tell us, and again for these ones sometimes you'll see the periodic table, it won't give you this 3a, 4a, but you're just really looking at this digit here, right? It's just this number minus 10 for all of these columns down here. But this number is telling you how many valence electrons that it has. So like in this one, carbon has 4 valence electrons, right? Oxygen here has 6 valence electrons, so on and so forth. And again, we're going to come back to these transition metals. Some of them will follow these, will kind of follow this rule, but for the most part, not really. And again, because of those 3D orbitals. Right now, we can just assume that whatever, if we look at the electron configuration here for any of these transition metals, it will be just the highest one, the highest energy level that it has, and you'd add up how many electrons. But for now, we're just going to focus on these elements here. Now, one last thing that leads me to electron dot diagrams. For electron dot diagrams, these are just a way to, these show valence electrons only. Valence electrons only. And so basically what an electron dot diagram looks like is this. Let's say we go back to here. Let's just pick a random element here. So we'll go with oxygen. Oxygen, which is in group 16, meaning it has 6 valence electrons. So what I would draw then for oxygen, the electron dot diagram, is I'm going to start with the symbol. So the symbol for oxygen is O, and then I just want to put, using dots to represent the electrons, I'm going to put those around this, basically. Okay. Oxygen has 6 valence electrons, we said, because it's in group 16. So we're going to go like this. 1, 2, 3, 4, 5, 6. So that's how we would fill in. There's my electron dot diagram for oxygen, showing that it has 1, 2, 3, 4, 5, 6 valence electrons. If I were to do the same thing for hydrogen, hydrogen is in group 1. It has 1 valence electron, and so electrons dot diagram would look like that. If I were to do it for magnesium, magnesium's in group 2, so it has 1, 2 valence electrons. If I were to do it for carbon, carbon has 1, 2, 3, 4 valence electrons because it's in group 14, and it would look like this. The most we can have is 8 valence electrons. So for our noble gases over here, these over here, they have a full outer shell of electrons. Full outer shell of electrons, which is 8 electrons in their outer shell. So except for helium, helium only has 2, which counts as a full valence shell because it's so small. But let's do like neon, for example. Neon has 1, 2, 3, 4, 5, 6, 7, 8, and that would be a full valence shell, would be all 8 electrons in that full valence shell. Remember, we said that that's why those noble gases don't react with anything, because they already have a full outer shell. These other ones don't, and so that's why they will either lose electrons or gain electrons in order to get a full outer shell of electrons, but we will get into that a little more later.